All right, so let's finish up this chapter 10 after our really not great morning. So I wanted to do a problem where you were reminded of how to do a cross product with unit vectors. I did make you watch that video again that I made at the beginning of the semester. So hopefully you're starting to get the hang of it. But the basic idea is that we're going to use a matrix and solve for the determinant of the matrix, and that will be our answer. So we're looking at the idea that torque is the cross product of R and F. Now, the way that we make our matrix is the top row is the unit vectors. And remember, a cross product is not commutative, so that means that you can't switch R cross F and F cross R, not the same. So we have to be careful about our order. So it had a little bit of problem over here with the transition to this program, but the radius vector in this problem is 6 meters in the z direction. So this would be the x component, this would be the y component, and this is the z component. That's for the radius vector. That's the second row. And then the next row is the force vector. It has an x component, a y component, and no z component. Now remember that we break down this, we expanded about the top row, and then the way that we figure out what the matrix is that goes by each unit vector is we would eliminate the row and column that that unit vector is in. The remaining 4 elements are going to be the elements that make up the matrix that's multiplied by that unit vector. So for the I hat, it would be 0 and 6, 3 and 0. There's an implicit negative sign by the j hat. Again, we eliminate the row and column that j is in. It's going to leave us with 0 and 6 and 4 and 0. And finally, the k hat direction. The determinant for that is 0, 0, 4, and 3. Finding the determinant of a 2 by 2 matrix is a lot easier because you multiply this way and then you subtract this product. So doing that, for the x component, we would end up with 0, and then we subtract 6 times 3. Then we have our j hat, we would have 0 minus 24. And then for k hat, you might have seen already, it's going to be a big fat 0. So in the end, our answer to the torque given by this force and this radius vector is minus 18I plus 24J, and the units of torque is Newton meters. And there you go. So now we're going to finish off with the last topic in this chapter, and that is, what is the rotational equivalent to F equals ma? Now, because you're such lucky students, I actually derived this expression on the video that you were supposed to watch for today. So hopefully you did, and you know that now we used a very specific example to come up with this idea where we had this mass on a table traveling in a circular path. We exerted a tangential force on that mass that would be perpendicular to the radius of the circle. And the nice thing about that is because then that force is producing a torque on the mass. And so remember I mentioned that F equals ma, if we sort of went along with our idea of what the equivalent might look like for rotational motion, we probably would guess that this would be the torque. The mass would turn into the moment of inertia, and the acceleration would be the angular acceleration. And it did turn out to be true. So that is a second law for rotation. And we're going to see that we could use that in some problems. There's going to be some problems that'll look very similar to ones we've done before, and then we could also there'd be new problems that we haven't seen before that we could use that expression. The latter is the first one we're going to look at. So in this problem, we have a flywheel. It has a moment of inertia of 50 kilograms meters squared. It starts from rest, so we know that omega naught is 0. And it's going to acquire an angular velocity of 200 radians per second. So and the reason that that's happening is because there's a torque that's being applied, and the time during which that torque is being applied is 5 seconds. So we definitely know that we're thinking of this relationship, the idea being that the torque is applied to the flywheel for a certain amount of time, and of course the flywheel has a moment of inertia. In this case, we were given what the value is. And obviously then, following from the expression and from just what we're told, this flywheel will undergo an angular acceleration. So that's the first thing that we're asked to find, is what is alpha. And for that, we can just use the general definition of alpha, that it's the change in omega over the change in time, which would be 200 divided by 5. And so that would be 40 radians per second squared. So now we found the angular acceleration that flywheel feels. And now they're asked what is the magnitude of the torque, and that's where we're going to use our new expression, where we take the moment of inertia, which here is 50 kilograms meters squared, times the angular acceleration, which is 40 radians per second squared, and this gives us a 2,000 Newton meter torque. And so that's how large the torque was that actually caused this to happen. So that's kind of a new type of problem that we hadn't seen before. That is, I think, a pretty obvious application of that rule. But I want to look at a problem that's a little bit more familiar to you, where we have two masses connected by a string hanging over a pulley. So we're going to change some things that we had done before, which might be a little frustrating, but we're going to talk about why. So we've done problems like this before, but if you think about it, we honestly ignored the pulley. That is, we didn't really factor it into playing a role in the problem at all. So now we're going to. If you remember, we often would talk about the pulley being frictionless. Another way to sort of think about that is that we were viewing the pulley, we weren't really considering its moment of inertia, that is, its resistance to rotation. And that's what we're going to do now. Now that we have sort of the tools to do this, we're going to see that this type of problem, we can think about the moment of inertia of the pulley and the fact that the pulley, obviously, as mass 1 falls because it's bigger and mass 2 rises because it's smaller, the pulley is going to rotate in the counterclockwise direction. And so as the objects undergo a linear acceleration, the pulley is going to undergo an angular acceleration. And our new rotational F equals ma, which is torque equals I alpha, is going to help us to quantify that, or actually to include that into our problem. So we're still going to use F equals ma for the two masses, but when we look at the pulley, we're going to use torque equals I alpha. Now, there's one last thing that I think might make you a little unhappy. When we did a problem like this before, we always assumed that the tension in the cord was the same throughout. But now that we're going to consider the inertia of the pulley and the fact that there must be some torque acting on the pulley, we can't say that anymore. The tension in the rope is going to be different in each piece. And so I'm going to call that T1 and T2, and then I have M1G and M2G. And so I'm going to look at the two masses first and apply Newton's second law. So for mass 1, I have T1 acts up, and its weight, M1G, acts downward. And mass 1 is accelerating downward, so the right-hand side should be minus M1A. All right, now I'm going to look at mass 2 and look at Newton's second law. In this case, I have T2 acting up, the weight of mass 2 acting down, and mass 2 is accelerating upwards, so that right-hand side can be positive. And so now, you might be concerned if you're thinking algebraically, because I have 3 unknowns, T1, T2, and A. But I have another piece of information. I can still work with the pulley. Now, when I'm considering the pulley, the tension in the rope acts on the pulley, and so I draw those tensions like that when I'm thinking about how they act on the pulley. And what I'm thinking about is not that tension as a force, but a force that's producing a torque on the pulley that's causing it to undergo an angular acceleration. Now I know that this pulley, because of the way the masses are moving, is going to undergo an angular acceleration in the counterclockwise direction. And I also realize, because of looking at the picture, that the torque caused by tension 1 is going to be greater than the torque caused by tension 2, because tension 1 is really the torque that's going to cause a direction of rotation that's counterclockwise. The torque due to T1 is T1 times the radius of the pulley. The torque caused by T2 is T2 times the radius of the pulley. Again, think about if I pull on the left in the direction of T1, I'm going to have a counterclockwise rotation. That's why that torque is positive. But if I exerted a force at like T2, which is on the right-hand side of the pulley, that would tend to cause a counterclockwise rotation, which is why that's a negative torque. So those are the two torques acting on the pulley. They're equal to the moment of inertia of the pulley and the angular acceleration. I'm going to ask you to assume that the pulley is a disk. And what that means is that its moment of inertia is 1/2 mr squared, where big M is the mass of the pulley. Now, I'm going to do one more thing before I start doing some big algebra. And you might be worried that I've introduced yet another unknown because of the angular acceleration. But remember, the angular acceleration can be related to the linear acceleration through a factor of r. So I can replace alpha by a over r. It's the same a that I see up here. I'm going to take the left-hand side of this and divide by r. So I get T1 minus T2 is equal to 1/2 mr squared times a over r divided by r. And so you should see that this is going to simplify to 1/2 ma. Now I can use these expressions up above to write T1 is equal to M1G minus M1A. T2 can be written as M2G plus M2A. And I'm going to substitute these two expressions into this equation. If I do that substitution, I have M1G minus M1A minus M2G minus M plus M2A is equal to 1/2 MA. So now I got M1G minus M2G, and I'm going to put all the terms that involve A on the other side. I'm going to 1/2 the mass of the pulley times acceleration plus M1 times acceleration plus M2 times acceleration. So I can then solve for A by factoring it out and then dividing by the term that in front of it. I'll find the acceleration of this system is equal to M1G minus M2G, and then divide by 1/2 M, the mass of the pulley, plus M1 plus M2. And that is how we can use this other term, the torque equals I alpha, in some problems that we've done before, but we hadn't done them in, we haven't included the inertia of the pulley, and this is how we do that. All right, so hopefully that's helpful. Hopefully Monday will go better and everything will work and we can move on and start chapter 11.